All right, so now we're going to take a look after we've seen several of the other gas laws, just simple ones, and we also saw the combined gas. Well, now we're going to take a look at something that is actually, you can think of it as sort of the ultimate relationship in when it comes to gases, and that is known as the ideal gas equation. And the ideal gas equation is actually a combination of all of the other gas laws um, that is going to describe the physical behavior of all gases. So we can essentially combine all of those relationships from Boyle's law, which is the inverse relationship between volume and pressure, Charles' law, the direct relationship between volume and temperature, Avogadro's law, direct relationship between volume and amount. You can combine them into a combined proportionality. So we can say volume is proportional to the product of the amount times the temperature divided by the pressure. And remember now, when we replace this proportionality symbol with an equal sign, we then need to introduce a proportionality constant. And usually we've used the symbol K for the proportionality constant before. Now we're going to use the symbol R to represent that constant, and then times NT over P. If we rearrange this equation, this is the same as saying R and T over P, move the P on the other side, then we end up with PV is equal to nRT. And this is probably the most important equation when it comes to gases, because it actually does have all of the other laws embedded in it, right? So sometimes this is to help you remember it. It doesn't sound the greatest, but sometimes people call it PERVNERT. Whatever you use to help you remember it, it's PV equals nRT. And R here is a proportionality constant that is called a gas constant. So it relates pressure, volume, amount, and temperature, all four of those different parameters that we saw previously. So this is called the ideal gas equation. It assumes a hypothetical sample of a gas where the pressure, volume, temperature, behavior can be predicted exactly by that equation. The gas constant itself, which is R, can take on different units, and these are listed here in table 11.4. When you're doing your performing your or doing your calculations involving the ideal gas equation, you're just going to use the most appropriate units. Okay, depending on what it is you're given or what it is that you need to find, okay, the numbers here, the numerical value all change depending on what information you're given in terms of pressure, volume, amount. So what we can do with the ideal gas equation is we can actually calculate the volume of 1 mole of a gas under a certain set of conditions. And we're going to refer to these conditions as standard temperature and pressure. And for our gases, right, this is where the STP comes from. For our gases, standard temperature is defined as 0 degrees Celsius, which remember is 273 Kelvin. And then for pressure, the standard pressure is defined as 1 atmosphere, which obviously can be converted to other pressure units depending on what it is that you're trying to find and what it is that you're given. So if we have those values, we can calculate the volume of 1 mole of a gas. So if we have PV equals nRT, I can rearrange this, solve for V. So V will be equal to N times R times T divided by P. Our N here is 1 mole. Okay, our temperature is 273 Kelvin. Our pressure is 1 atmosphere. And then we're going to use the unit for R that has moles, Kelvin, and atmospheres in it, right? And that is the 0.08206. The units here are liter atmosphere per mole Kelvin. Okay, so we can see now moles go away, Kelvin goes away, atmosphere goes away. We have liters as our unit. And if you plug that into your calculator, you will see that the answer is 22.41 liters. This is known as the molar volume of a gas. And we can use that as a conversion factor. We can say 1 mole of any gas is equal to 22.41 liters. And the thing about this relationship, right, that's our molar volume, is that it holds true at STP conditions for any gas there is. Okay, which actually tells you the identity of the gas is going to be irrelevant. All that matters is that you have a mole of it and you have that sample in the gas phase. So we can also use the ideal gas equation to relate other properties of our gases. So for example, if you have our PV equals nRT and we rearrange this equation, we can end up with, so if we divide, let's say, the left side by V and the right side by V, if V's go away, we end up with P is equal to N RT over V. And then if we divide now both sides by RT, then we end up with P over RT is equal to N over V, right? So we know that N there is a number of moles, V is equal to volume. Well, if we take the molar mass of a gas, so molar mass is in grams per mole, okay, and if we multiply the molar mass by N over V, okay, so if we look at our unit, grams over moles, N here is the number of moles, so the moles are going to cancel. We end up now with the grams over volume is equal to, that would be equal to pressure over RT times the molar mass. Then grams over volume, that's the same thing as the density, right? Grams here is mass, and V is volume. Okay, mass over volume is the density of a substance. So we can actually relate the density that's entire left side here. The density is equal to the pressure times the molar mass, which we'll abbreviate as M, funny looking M, divided by gas constant times the temperature, and again, our density there is in grams per liter, and the molar mass, as usual, is in grams per mole. So we can relate using the ideal gas equation. We can do a little bit of mental gymnastics, and we can now relate the density of a gas to the molar volume of that gas. You see an example down here. So what pressure would be required for helium at 25 degrees Celsius to have the same density as carbon dioxide at that pressure and that temperature, right? So if you have a question like this, you want to first of all determine what is the density of the carbon dioxide. You need to get the density of the CO2 using that equation. That'll be equal to the pressure that it's being subjected to times the molar mass of CO2 divided by gas constant times temperature. So the pressure is given, that's 1.00 atmospheres. The molar mass of CO2, right? We should be able to do that right now. Oh, I should be good at doing that at least. That's 44.01 grams per mole. R, or gas constant, 0.0821 liter atmosphere per mole Kelvin. And then our temperature here is 25 degrees Celsius, so we add 273, that's 208. Kelvin goes away, moles go away, atmospheres go away. We end up with grams over liters as our unit, which is our density. So that makes sense. That's what density of CO2 here would be equal to 1.00 say 7966 grams per liter. So what we need to do is to figure out what pressure would be required for helium to have at 25 degrees to have that volume. Right. So now this should also be the density there would be is what we're looking for. The density now of helium needs to be the same as the density of CO2, so that's 1.7966 grams per liter. Then we have the pressure, is what we are trying to find. That's our unknown in this problem, times the molar mass of helium. Divided by gas constant times temperature. Right, so we have 1.7966 grams per liter equal to the pressure, which is our unknown, times 4.003 grams per mole divided by 0.0821 liter atmosphere per mole Kelvin times the temperature, 298. Kelvin goes away, moles go away, and our grams and liters cancel out on the other side. We end up with atmospheres as our unit. We stick that into a calculator, we solve it for P, and we end up with P being equal to 11.0 ATM. So as you're seeing now, as with the other examples, the majority of the gas laws really just boil down to doing a bunch of math, right? It's algebra that we're doing, substituting, rearranging, and solving, but knowing where the information comes from, picking out the relevant information is going to be critical when we solve our gas law problems, whether they are applications of the ideal gas equation in terms of density, or whether it's just using the ideal gas equation, or whether it's using any of the other gas laws, the simple ones or the combined ones. Half the battle there is just figuring out what information we're given and what it is that we need to find.